imagine, if you will, a material. Maybe for a spacecraft, something that has to handle just extreme conditions.
Extreme heat, radiation, the works.
Exactly.
Yeah.
But what if it could also sense if it was damaged? Like tiny microfractures.
And then what?
And then repair itself in real time.
Okay, that sounds like something straight out of science fiction.
Doesn't it? But today, we're diving into a report, a really comprehensive one, outlining how this impossible idea might actually be feasible. It's based on a hypothetical sixth element composite.
Sixth element. Intriguing.
Our mission here is to unpack what makes this material truly multifunctional and, how it could potentially shake up industries like aerospace, maybe defense, energy.
Good stuff.
Definitely. So, okay, let's start unpacking. This material, it's made of 6 distinct components working together.
Right. A team effort.
What are these players and how do they mesh to create something, well, better than the individual parts?
Yeah, it's a fascinating mix. We're talking tungsten, titanium, silicon, bismuth, aluminum, and quartz cyories.
Okay. Quite a list.
It is. And the key insight really is the synergy. Each one is chosen to kind of balance out the weaknesses of the others.
Right.
Take tungsten, for example. It's your structural backbone. Phenomenal high temperature stability, highest melting point of any pure metal, actually. Over 3,400 degrees Celsius.
Wow.
But the downside is it's notoriously brittle on its own.
Okay, so it needs help.
Exactly. And that's where others come in. But what's really clever, I think, is how they use bismuth.
Bismuth. Isn't that used in, like, Pepto-Bismol?
Ah, well, yes, but it's also a heavy metal. Great for radiation shielding. It's dense, like lead, but non-toxic. That's a huge plus for medical uses, space applications.
Non-toxic shielding. Okay. That's useful.
Definitely. But here's the twist. Bismuth has this incredibly low melting point, just 271 Celsius.
Which sounds like a bad thing for a high-temp material, right?
Usually, yes.
Like
Total liability. But in this concept, it's actually a strategic asset. I'll get to why in a bit.
Okay. Intrigued. You mentioned quartz, too.
Ah, yes. Quartz. See, that's really the game changer here. It's what elevates this from just a strong, heat-resistant composite to something intelligent.
How so?
It brings piezoelectricity into the mix.
Piezoelectricity. Okay,
Yeah.
Now this is where I really start to wonder. How on earth do you make this?
Yeah.
You've got tungsten needing thousands of degrees, bismuth melting practically in a warm oven. You mentioned aluminum and bismuth don't even like to mix.
Immiscible. Yeah.
It just sounds like a recipe for disaster if you try conventional methods. Like,
Right.
wouldn't it just clump up or, I don't know, react badly?
You've nailed the core problem. Absolutely. Conventional casting, forget it. You get terrible segregation, unwanted reactions, just a mess.
So what's the secret sauce then?
The proposed solution is really quite innovative. It's a specific type of additive manufacturing, or 3D printing, basically. They call it bismuth-facilitated powder metallurgy, BiFPM for short.
Bismuth facilitated. Okay, break that
great.
down.
It's a 2-stage process. Think of it staged. Stage 1 happens at a low temperature.
Using the bismuth?
Exactly. You have a powder bed with all the components mixed together, tungsten, quartz, everything. Then you heat it just enough to melt the bismuth, only 271 degrees C.
Ah, so the bismuth acts like a temporary glue.
Precisely. A liquid binder. It flows around the other powders, locking everything in place uniformly without causing those high-temperature reactions or damaging sensitive things like the quartz.
Clever. Okay, so you get this sort of loosely bound shape.
Right, what's called a green body. Then comes stage 2. You take that green body and heat it much higher.
To handle the tungsten and other metals.
Yeah. This stage is about consolidation. Sintering. It densifies the stronger metallic phases, giving the material its final strength. It's kind of analogous to how they make tungsten-heavy alloys already.
So it sidesteps the whole melting point conflict by doing it in steps.
It elegantly solves that core fabrication paradox. It's a way to build the material layer by layer, controlling the process at each temperature stage.
Okay, that makes sense. It's pretty ingenious, actually. So after all that clever manufacturing, what's the payoff? What can this sixth element composite actually do?
Well, this is where it gets really exciting. The payoff isn't just, being strong or handling heat. It's the multifunctionality, the smart aspect.
From the quartz, the piezoelectric thing.
Exactly. That embedded quartz is key. Piezoelectric means it generates an electrical signal when it's squeezed or stressed mechanically.
Okay.
And crucially, it's non-pyroelectric, which means temperature changes don't mess with that electrical signal. Very important for thermal stability in extreme environments.
Right, you wouldn't want false readings, so what could you do with that effect?
A few amazing things. Imagine passive vibration damping the material itself could dissipate harmful vibrations, maybe in an engine or airframe.
It's absorbing the energy.
Essentially, yeah. Then there's self-sensing. The material can tell you in real time about its own condition. Is it under stress? Are there microcracks forming? Structural health monitoring baked right in.
Wow. No need for extra sensors, maybe.
Or fewer, certainly. It could even power tiny sensors, energy harvesting, converting ambient vibrations, the very ones that might be damping, into electricity.
Okay, that's seriously cool. A material that powers its own monitoring system.
And don't forget the other baseline stuff. You still have that excellent high-temperature performance from the tungsten matrix and that non-toxic radiation shielding from both tungsten and the high-density bismuth.
Right, the lead alternative.
Exactly. So connect all that together. You're looking at a material practically designed for the toughest jobs: jet engines, rocket nozzles, next-gen reactors, deep space missions.
Yeah, anywhere it's hot, high stress, maybe radioactive.
Mm-hmm.
This material could potentially thrive.
That's the idea.
This really opened my eyes. It's not just a structural material. It's an active system, a sensor, a damper, even a power source.
It really shifts the paradigm, and, it pushes us to ask, what else could materials do? The most provocative idea floated in this report, I think, is taking it one step further towards self-repair, true self-healing.
Using the bismuth again.
That's the concept. The piezoelectric quartz senses a microfracture starting. It sends a signal. Locally, maybe through targeted heating or just the stress concentration, that low-melting bismuth phase is triggered to melt and flow into the tiny crack.
Like bleeding to form a scab.
Sort of. It would essentially heal the damage autonomously, potentially massively extending the lifespan and reliability of the component.
A material that detects its own flaws and then just fixes itself.
Imagine that. Materials that don't just endure, but maybe even think for themselves in a way.
That's incredible. What could you, listening right now, do with a material like that? A component that knows it's damaged and repairs itself.